12 days ago, NASA quietly uploaded a new analysis that did something most headlines about alien life never do. It made the story less exciting on purpose, because that's what the actual data supported. The planet at the center of it all is called K2-18b, and by the end of this video, you'll understand why some of the most credentialed exoplanet scientists on Earth still can't fully agree on what its atmosphere is actually telling us. K2-18b orbits a red dwarf star roughly 124 light-years away in the constellation Leo. It's substantially larger than Earth, about 8.6 times the mass and 2.6 times the radius, placing it in a category of planet we don't have any direct example of in our own solar system. Something between a rocky world and a small gas giant, generally called a sub-Neptune. Critically, it orbits inside its star's habitable zone, the distance range where temperatures could theoretically allow liquid water to exist on a surface, assuming that surface exists at all in any recognizable form. The story of what makes this planet special goes back further than most people realize. In 2019, researchers first detected water vapor in its atmosphere, a genuinely exciting result at the time, and one of the first such detections ever made for a planet sitting inside a habitable zone. Then, in 2023, the James Webb Space Telescope detected methane and carbon dioxide there, alongside something notably missing: almost no ammonia at all. A team led by Nikku Madhusudhan at the University of Cambridge argued that specific combination pointed towards something called a Hycean world, a hypothetical class of planet with a hydrogen-rich atmosphere sitting on top of a deep, global ocean of liquid water, an entirely different architecture from anything in our own solar system. Low ammonia specifically matters here, because ammonia dissolves readily into liquid water, so its near-total absence from the atmosphere hinted that a vast ocean might be quietly soaking it up from below. That same 2023 data also contained a faint, low-confidence hint of something else entirely: dimethyl sulfide, usually shortened to DMS, a gas that on Earth is produced almost exclusively by marine phytoplankton. Nobody treated that early DMS hint as remotely conclusive at the time. It was too faint, too uncertain, sitting right at the edge of detectability. The kind of signal that shows up and disappears again, depending on exactly how you process the noise around it. Then, in April of 2025, Madhusudhan's team returned with new data, this time gathered using JWST's mid-infrared instrument, covering a wavelength range from 5 to 12 microns. Their analysis reported a 3 sigma confidence detection of DMS, dimethyl disulfide, or both, in K2-18b's atmosphere. In statistics, 3 sigma results are treated as suggestive, not proven. But this was still a substantial jump in confidence from the near-invisible signal spotted 2 years earlier. And it was the first time this specific pairing of molecules had ever been proposed as a potential biosignature on any exoplanet anywhere. Here's a detail that tells you almost everything about how the scientific community actually received this claim. When earlier JWST results about K2-18b came out, NASA had issued public press releases promoting them, the standard treatment for a genuinely exciting result. For this specific April 2025 result, they didn't. Instead, the agency released a more cautious statement roughly 2 weeks later, emphasizing that confirming a genuine biosignature would require follow-up studies and multiple converging lines of evidence, gathered from independent missions, specifically designed to rule out every plausible false positive first. That's not the language of a discovery being celebrated. That's the language of an agency being deliberately careful about a claim it wasn't ready to fully endorse in public. What followed was rapid, public, and genuinely rigorous scientific pushback, playing out across multiple independent research teams within weeks of the original announcement. Louis Wellbanks, a postdoctoral researcher at Arizona State University, argued that the original Bayesian statistical comparison didn't actually translate into a robust detection the way it had been presented, and demonstrated that other molecules entirely, including a hydrocarbon called propane, fit the same data equally well, meaning the statistics alone couldn't actually distinguish between a biological explanation and a purely chemical one. Jake Taylor ran a more basic test, checking whether the mid-infrared spectrum showed any statistically significant features at all, using what's called a flatline rejection test, and found none, essentially questioning whether there was a real signal there to explain in the first place. A team led by Kevin Stevenson went further, reprocessing the raw JWST data using several different, independent methods and wavelength binning schemes. In their preferred configuration, 87.5% of their reanalyzed results showed no significant evidence for DMS or DMDS whatsoever, though they did confirm methane at high confidence. Separately, a team led by Raphael Luke combined 3 different JWST instruments into one full, panchromatic spectrum spanning the entire relevant wavelength range, and still came away without sufficient evidence to support the original biosignature claim, noting that several other molecules containing methyl functional groups fit the combined data just as well as DMS did. Then came the July 2026 update that reopened the whole conversation. A new NASA-led analysis, uploaded as a preprint on July 16th, confirmed that K2-18b genuinely does have a water-rich, chemically complex atmosphere. But on the specific question of DMS or DMDS, the team found no conclusive evidence either way, explicitly underscoring just how difficult these particular signals are to interpret with any real confidence using current instruments. Even years and multiple independent reanalyses into the debate. It's worth pausing here to explain why this argument is happening at all, instead of just accepting the original result or dismissing it outright. The core disagreement isn't about whether Madhusudhan's team saw something real in the raw numbers. It's about whether the statistical method used to interpret faint, noisy mid-infrared data can reliably distinguish one specific molecule, DMS, from a whole family of chemically similar alternatives that would produce a nearly identical signal in this kind of instrument. Every team involved in this debate agrees the raw JWST data is valuable and worth continuing to study. They simply disagree, using rigorous competing statistical frameworks, about what that specific data is actually capable of proving right now. At this exact level of instrument sensitivity, a survey published in Nature Astronomy captured just how unsettled the broader scientific community remains on this question. Among astrobiologists directly surveyed about the claim, only 6.6% agreed that scientists had probably found extraterrestrial life on K2-18b. That's not a field split evenly down the middle. That's a field where the overwhelming majority view the original claim as, at minimum, seriously premature, even while taking the underlying data completely seriously. None of this makes K2-18 be a failed story or a wasted opportunity for the field. Quite the opposite. Every reanalysis, every competing statistical framework, every independent team pulling the same raw data through a different pipeline, has done exactly what good science is supposed to do. stress-test an extraordinary claim before anyone is allowed to treat it as settled fact. K2-18b remains the first sub-Neptune more than 100 light-years away, where astronomers have managed to build a genuinely detailed atmospheric picture at all, complete with confirmed methane, likely carbon dioxide, and a real, ongoing argument about trace gases that could, in principle, mean something profound about the possibility of life beyond our own solar system. Whichever side of this specific debate turns out to be right, both sides are chasing the exact same underlying question. What would it actually take to prove, beyond reasonable doubt, that we found life somewhere else, using nothing but light passing through a distant atmosphere? K2-18b hasn't answered that question yet, but it's forced the entire field to spell out, in exhausting, rigorous detail, exactly what real proof would eventually have to look like, and that's not a failure. That's the first real draft of the standard the next claim, wherever it comes from, will actually have to meet. Beyond the visible, beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel, new episodes on space, physics, and the edges of what we understand, with new content going up every day.